Yeah, so what I want to say is like, so when you have like, say Ka, and you want to, if it's divisible by P, right? If P divides that.
Yeah.
Like, is it clear to you that if P is prime, then P has to divide either K or P has to divide A?
Yeah.
Because prime, right? That's one of the key properties. So, but remember the K's that we had, it was like A, 2A, P, PA, right?
Mm-hmm.
So all the A's that we had, well, they were less than. So the P, if they were dividing that, they had to divide A, right?
Yeah.
Yeah. So and if it divides A, then all these like Ka on P just becomes Ka on P, right? Because it divides it, so there's nothing to cut off. Yeah. Okay. So I think it's really easy to do it in that case, right? You just equate it to 100, and you get a formula. Yeah. So the problem is, what happens if P does not divide Ka? So basically, it's the same thing as saying P does not divide A, right? So what I'm trying to say is, like, suppose so for example, think if A has remainder 1 when you divide by P, yeah. Another way of saying that is A equals 1 mod P, yeah. And then what's 2A, you know? It's 2 mod P, right? And the point is, the remainders of all these different numbers, 3, 4, 5, all the way up to P minus 1, right? It's just going to be P minus 1. It's just going to be the number.
Yeah.
Does that make sense? So like, if you look at, if you look at them individually, you might not know what's going on. But if you do them all at once, if you add them, see, like if you do A over P plus 2A over P, right? Plus P minus 1 A over P, right? That's going to give you, it's going to give you this, right? So that's like if you don't have the floors. Yeah?
Wait. So you know how the coefficient of A will be the remainder?
Yeah, like, so if we assume, like, if we assume that A is 1 mod P, then basically the coefficient of A is the remainder, yeah?
Yeah, then like you have the remainder with like 1, 2, 3, 4 all the way to P minus 1.
Yeah.
But then like, oh wait, never mind, we can't.
Yeah.
Yeah.
So that's kind of the point. Like, so I mean, this is what it would be without the floor, right?
Mm-hmm.
Like, what is the floor actually doing?
Actually,
It's minusing 1 over P from that, right?
Yeah.
It's minusing 2 over P from that. You know what I mean?
Mm-hmm.
So that's what the floor is doing. Yeah. So then this is equal to this.
Yeah.
Right? If you know the remainders of 1, 2, 3, 4.
Yeah.
Okay. Actually, it's not actually too far from this. You know that, so what you do know is that all the remainders are all different.
Yeah.
Okay. And for them all to be different, and there's P minus 1 of them, right? Then they have to have them in some different order.
Yeah.
Yeah. So they might not be in this order, but the total will still be the same.
Yeah.
Okay. Does that make sense to you?
Mm-hmm.
Is it clear to you that, so basically like Ka, right? And La, yeah.
Mm-hmm.
Like they can't have the same remainder unless basically K and L are the same.
Mm-hmm.
Do you understand why?
Yeah.
It is. It's because, yeah, like for example, if you want to prove it, right?
Yeah.
If they're the same mod P, yeah? Then you could subtract them. So basically, K minus L times A is 0 mod P. So basically all you're saying is that this is divisible by P, right? But P does not divide A, so it has to divide K minus L.
Yeah.
Right? But K and L are both from 1 to P minus 1, so K minus L has to be 0, right?
Yeah.
Does that make sense?
Yeah.
Like it can't be P because this is too big. This is not even up. This is not even P. This number is between like negative P and P, right? So if it's a multiple of P, it has to be equal to 0,
Yeah.
right? So you can't have two different remainders mod P. So therefore all of these have to occur somewhere, but in a different order.
Yeah.
Does that make sense?
Yeah.
So then what you get, so then this is actually the formula. So, so if we have the sum of Ka over P, right? K equals 1 to P, yeah. That basically equals the sum Ka over P minus the sum of these, yeah? So this is K. Does this make sense?
Yeah.
So you got rid of the floor, yeah?
Yeah.
And so remember, we know what that is, yeah? We know that that formula is, it was, A outside of P plus 1 on 2, right? And this is, well, this is P outside of P minus 1 on 2P. Yeah? Oh, and I guess there's a plus P somewhere, maybe. Yeah. Yeah. So this is meant to be equal to 100, right?
Yeah.
Remember?
Yeah.
Yeah, so then 200 is equal to, the p's cancel here, right? Yeah. And then you can cancel the 1. So 199 equals, 199 plus P equals AP plus 1, right? So now basically, now anytime A is an integer, so anytime this is divisible by that,
Yeah.
you'll get a solution, right? So for example, remember how we said 197 worked?
Yeah.
So what happens if it's 197? Well, this is, 396 equals, well, A outside of 198, right? So A is equal to 2. So if A is an integer and P is prime, then it works.
Yeah.
So basically the question becomes, find all the primes such that A is an integer in this equation. Does that make sense?
Yeah.
Can you do that easily? Yeah, take your time. This could be a question on its own, actually. That could be, depending on your experience with these kind of questions.
I factorized it. Like,
Oh, how did you do this for me?
so I got so I did AP plus A minus P. I factor it like factorize so P plus 199 equal to AP plus A.
Oh, you expanded it?
Yeah.
Mm.
And then you put P to the other side.
Oh, okay. That side? Like 1 minus A? Is that what you're doing? Or?
So I put minus P from that side. So I did AP plus A minus P is equal to.
Oh, okay. Uh-huh.
Factorize AP plus A minus P. So
Oh, can you? Okay, well, what is that?
A minus 1 times AP plus 1. No, minus 1 times P plus 1.
Oh, that's really good.
Then you have to minus 1 plus you have to minus 1 to the other side. So 198 is equal to A minus 1 times P plus 1.
Oh, I see, yeah. So, you did a minus 1, so... Okay, well, that's good. That's very good. So then you just have to factorize 198, right?
So it's 2 times 3 squared times
2 times 3 squared times 11, yeah? Yeah. Yeah, so that's a really good way to do it. Another way that you can do it to get to this point, that's quite common, is you probably know it. You can write A as P plus 199 and P plus 1, and then you can just make this 198 plus 1. So you get 1 plus 198 on P plus 1. So you see how you get the same thing. The whole point is whenever P plus 1 divides 198 is when you get an integer for A, right? Or if you rearrange it, that's A minus 1 times P plus 1, right? Yeah. Okay, so here, there's not that many primes at work, right? Yeah, so on Friday, if they ask, you have to explain it to them because I won't explain it twice. But yeah, hopefully it's good. Yeah, so it's good to confirm that the ones we had before work, right? Like 197, p equals 2 works, right?
Yeah.
5, does 7 work? No. Yeah, so the ones that worked before work now, and they don't work still, right? Because you could have easily made a calculation error to get to that step, but it's very unlikely if the examples work.
Oh, but for some reason I only got like when I did it, like made it, only got
3 p's.
4 p's.
Which ones?
2, 5, 17, 197.
2, 5, 17, 197.
Yeah.
Yeah, what's wrong with that?
Oh, it's something wrong.
Yeah, I mean, there's not many possibilities, right? If p is 2, then that'll be 3, and that'll be the other stuff, right? But if p is not 2, then it has to have the 2 as a factor, then, right? There's only so many ways you can factorize 3 squared times 11. You know, you can't have 3 squared. Yeah, you can have 3 squared is 9, and you get 18, right? That's where 17 comes from. Okay, you can have, so you can't have 3 times 11, right? Because that would give you like p equals 65. And so then the only other ones left is like 3 squared times 11. That gives you 197, right? And then 11 by itself, because 21 is not prime, you don't get anything, you know? And then, yeah, 3 by itself, that's what gives you 5, yeah. There's not many ways you can pick 2, like, you can make factors with 3 primes, right? Especially if 2 of them are the same. Yeah. So I was saying, like, to do it the long way, I think is fine in like a normal context, but in an exam time setting, you might need to find something like this to do it in the time limit. Yeah. Yeah, I mean, we didn't have any other primes that worked, right? Last time. We just had 2, 5, 197. Because all the ones that we had that worked were like a square plus 1. And so I guess it's nice that 17 worked. Yeah. Let's focus on some other problems. Do you want to take me through this problem? Do you still remember how to do it?
Kind of. I don't remember the steps.
Yeah, you can show me. Yeah, can I explain it? Alright. Yeah. So it's like the nth triangle.
So, molecular. So it's when I'm trying to find the equation for the triangle numbers, it's like 1 plus a plus
1 plus 2, oh, plus 6.
because of that and it keeps on going. And then plus 10 and it goes on. And this, I think this can be expressed to the form 1 plus 2 plus 1 plus 2 plus 3 plus
Yeah.
Then you can see a question there.
So the first thing you wrote up is capital T4, is that right?
T8. See, does it go up good?
Up to the, yeah.
Yeah.
Right. I guess little t and then also. Or you can even write the formula in like n. Is it n times n plus 1 or 2? Yeah. It goes all the way up to like n times n plus 1 or 2. Yeah.
Yeah. So the Tn is equal to that. Got all the way up to, let's say, like x.
You can write the formula like so. You can write n times n plus 1 on 2. Oh, sorry, on the whole thing on 2. Not the last bit, yeah. Oh no, sorry, the whole thing over 2, like n times n plus 1, and then all over 2. Yeah, that's it. Good.
Okay, shouldn't that be for that? Because it's like 1 plus 2 plus 1 plus 2 all the way to.
Yeah, so because I mean, like 3